Hi, everybody. Today we're going to talk about methods of heat transfer. There are three main methods of heat transfers. I'm going to talk to you about. My belief is there's actually only two, but we'll get to that as we move along. If you were asked this question on a test from anybody other than me, you would write down three. That's the general standard. But as I'll explain to you, a physicist doesn't believe that convection is real. As we move along, we are going to talk about start off with conduction. Conduction on an atomic scale is the exchange of energy through collisions. It's a conservation of energy by interaction of the change in momentum. Remember, we talked about heat as being momentum. So if there's a collision of particles, one particle slows down, one particle speeds up. So there's a change of energy in that process as well. And so the rate of conduction depends on the type of materials, how readily the particles can collide, their ability to absorb heat, their specific heat. And so conduction is ultimately about direct contact and how we can make the particles transfer that energy quickly if we want to have a good conductor. An example is this hot plate that's on your right here. We have the molecules vibrating because of the resistive heat of the electrons as they were traveling through the wire. It's an electrical circuit. The coil is high resistivity, and so as the coil is having electricity run through it, you're getting a lot of resistance and a lot of heat. That causes the coil itself to heat up. The coil's heating up. It's causing a collision of the molecules between the pan and the coil itself. Then whatever's in the pan is going to be in contact with the pan. And so if it's water, for example, in the pan, the water molecules will start to vibrate because the pan molecules are colliding against them. And so you have this collision from electrons to the metal, the rest of the atoms of the metal to of the coil to the metal of the pan to the water. Direct contact, the vibrations are just collisions that are occurring between these objects. The rate of conduction is determined based on, it's a power equation. The rate of conduction is the amount of energy per unit time. And what affects that are four things. I guess really it's three things, and then that leads to the change in temperature. This is how we would figure out the rate of conduction. But what matters is the cross-sectional area, how big the object is, depending on the size of the object, the face of the object, the more energy will be transferred because there will be more particle collisions. If I have a wall that's highly insulated and a small window, there's very little energy transfer out that window. If I have a big window and the same wall, there could potentially be a higher rate of transfer of energy out of that window because there's a greater cross-sectional area. The other things that affect it are what we're going to refer to as the conduction constant. That is a constant that is determined by the property of the materials. Some materials have a higher level of conduction. Some have a lower level of conduction, which means they have a higher level of insulation. And then the thickness. That's what L is. And the thicker this is, the less energy transfer we're going to experience. And so when I put insulation into a home, we can get R13, R20, R30 insulation. All that's going to be is the thickness. The greater the number, the greater the thickness. It's made out of the same material, so it has the same K value. The wall of your house has the same cross-sectional area. So what we do when we get a higher level of insulation is we just make it thicker. And our insulation in our homes is dependent on the wall size. Most homes have a 2x4 wall, but if we put in there a 2x6, a 6-inch board, we get an extra 50% of distance, which ultimately leads to extra insulation. It costs more upfront to build a house with 2x6 studs, but they can pay for itself over the longevity of the home because you're going to save money on the heating costs. And then this is the difference in temperature between the high and the low side. So if there's no difference in temperature between the high and the low side, you can't have a flow. But if there is a great difference between the high and the low side, then you will have a flow. This is, I want to say, a property of the material. In the beginning, if you go back, I said something about there's 3 variables. This is a property of the environment that the material is in. And so again, the greater the difference between TH and TC, the high side and the cool side, the inside of the home and the outside of the home on a winter day, the greater the ability for the energy to flow out of the home. Again, if the inside's hotter than the outside, the energy is going to flow out. If the outside is hotter than the inside, the energy is going to flow in. Same effect by the insulation and thickness and things, but there will be a greater flow the greater the difference of energy. And you could see here, this just explains some of the things I just mentioned. There's an equation that describes the R value. The R value that we find in insulation is the thickness divided by the constant of the material. And so we can have insulation R values. So an R since the insulation is the same material, K value is the same. To get a bigger R, we just have a bigger thickness. If I have multiple materials, there's an equation. I will not ask you to know this equation. I'm not going to ask you anything about this, but I want you to know that if you did need to do multiple materials, there is a way to do that. The second form of energy transfer is convection. Convection is the movement of energy in the form of heat by fluids and only in fluids. So with this, convection will not work in solids, but energy transfer by the movement of the substance. We talked in the last video about the wind currents, but that is how this is going to work here. If I have, for example, this hand over top of the fire, the hot air rises, and that is a convection process. The air above the hand is warmed up. Another examples or applications of this are boiling water radiators. You can see all the different types here. And here is your traditional heating model. The energy here is coming out of the radiator. This could be anything. It could be a firebox. It could be a propane heater. It could be a number of things. But ultimately, there's heat coming from here. The hot air rises. There's a void because if the hot air rises, something has to come in there. So it's almost like a vacuum pulls in. So the hot air rises. As it moves over here, it's cooling down, so it gets sucked back down. And so you get this circular pattern. This is called convection. I would argue that what we have actually happening here is that we have direct contact or conduction between the air molecules. And then because the air molecules expand and become less dense than the surrounding air, because they're hotter, they rise. So it's a conduction with Archimedes' principle. That's how you can think of convection. And so when the air molecules cool down, they settle because they become more dense, and then they end up going back through that process. So we have a conduction with a Archimedes principle or convection. It would all be described the same way. 2 ways of arguing the point. The last point is radiation. Radiation occurs by waves of energy traveling through, for example, a vacuum. Here we have a radiation that we can think about it as coming from the sun. And there are laws such as Stefan's law that describe how much energy is being transferred. It does not need a barrier. It does not need air or water. It can travel through the vacuum. It is an electromagnetic wave carrying energy. When it strikes the hand, or the body, you feel warmth. The equation for this is on the screen in front of you. The rate of energy transfer is equal to the constant, the radiation constant that you can see here. A, which is a surface area. E is a constant called the emissivity constant, which describes how effective the radiation is happening. 0 would be not at all. 1 is being perfect. And T is the temperature in kelvins. And notice this is the fourth. There's very few equations you have that have T to the fourth. That equation here gives you the power at any given point. Now, what we really care about is whether energy is absorbed or emitted. And so what we can look at here is the change in temperatures. So it's a similar equation, but when we're looking at this, we're looking for how how the power is affecting change. And so if we have an equilibrium, there's going to be no flow at all, and the temperature ultimately won't change. There are ideal absorbers and ideal reflectors. An ideal absorber has an emissivity constant of 1, and an ideal reflector has an emissivity constant of 0. Think about a concrete blacktop. If you go outside on a hot day, you can walk along a concrete sidewalk because it has a emissivity constant that is low and it reflects off a lot of the energy. Well, if you go out on blacktop, it is very hot, and that's because the black absorbs the energy, and therefore it has an emissivity constant close to 1. This leads to something called blackbody radiation, which we'll talk about at a later point. But just a quick synopsis: blackbody radiation says when heated, an object will glow at a specific frequency, so a specific color, depending on the heat it's at or the temperature it's at. And we will discuss that more down the road. There are many applications to radiation, from clothing to thermography to body temperature sensors. We've all experienced some sort of measurement, some sort of measurement of our temperature. I'm sorry, I just lost my thought there. Some sort of measurement of our temperature with a infrared radiation. That's actually pretty much what they're doing now as you're walking into school. Ultimately, conduction, convection, and radiation can be summarized using what we call the Dewar flask. You're going to learn a little bit about James Dewar as we're watching the Absolute Zero videos. But Dewar's flask, which is similar to a coffee mug, has a very specific design. One, it has a silvered inside surface, which makes the inside like a mirror. That will allow anything that's radiating out of the object to radiate back in, so you get that reflection. The second thing is that there is a vacuum in it. That vacuum, the white area in there between the inner and outer wall, creates the ability to stop convection and conduction. If it's a vacuum, there will be no direct contact, and so that means that conduction and convection can pretty much be stopped. And so together, using these principles, we were able to create a pretty good thermos that will keep stuff either hot or cold. This concludes our discussions on conduction, convection, radiation. If you have any questions, please let me know.